All right, welcome back to Numerical Analysis. Today we're going to start talking about power series solutions for ordinary differential equations. And I'm going to try to keep this one kind of short, so this will be part one of a series of videos on this topic. Um, the first thing we want to do is rather than just try to jump right into the solution, we're going to try to see what information we can pull out of an ordinary differential equation, especially in the context of a initial value problem. So here I have a little initial value problem that I want to use to sort of illustrate the idea. Obviously, we have information here about the function x and its derivative. The derivative of x is 2 times x itself. That's the ODE part. And then the initial condition here is that when time t equals 0, x is 3. So x of 0 is 3. So actually this is a pretty easy one to solve. You may in fact already kind of recognize what the solution is, but I really want to hold off on that for a minute, and I want to talk about just some very direct information we can pull straight from the initial value problem itself. So for instance, we clearly know that when t is 0, x is equal to 3. But the differential equation also allows us to know something about the derivative. So, for instance, if you wanted to see what the derivative was, x prime at time t equals 0, well, that's just dx dt evaluated when t equals 0. And then going back up to the ODE part of the initial value problem, we know that dx dt is 2 times x. So dx dt evaluated when t equals 0 is 2 times x evaluated when t equals 0. But when t equals 0, we know what x is, and that's from the initial condition. X of 0 is equal to 3. And so putting all that together, we see that x prime of 0 is 2 times x of 0, or 2 times 3. I'm going to leave it that way because, as you might expect, a pattern is going to develop, and a lot of times it's easiest to see the pattern if you don't do a lot of simplification. So there we see that the derivative of x at time 0 is also known from the ODE. But you can go further than that. You can also get second derivative information. So how would you do that? Well, the second derivative here, d squared x dt squared, is just the derivative with respect to t of the first derivative. But dx dt we already know is 2 times x. So we have the derivative with respect to t of 2 times x. Now here you need to remember that x is a function of t. So when you're taking derivatives, you got to keep that in mind. So the derivative with respect to t of 2 times x would be 2 times the derivative of x with respect to t. And now we can go back to the ODE again and replace dx dt by what we know it's equal to, namely 2x. So putting all that together, we get 2 squared times x. So the second derivative of x with respect to t is equal to 2 squared times x. And now we can find the second derivative evaluated when t equals 0 in the same way as before. The second derivative when t equals 0 is just our second derivative evaluated at t equals 0. So that was 2 squared times x evaluated when t was 0. And we know that x of 0 is 3 again, and that's from the initial condition, so we get 2 squared times 3. So now we have information about the second derivative at 0. And this process continues. So if we look at the third derivative, what is that? Well, it's the derivative of the second derivative. And we just found previously on the slide that the second derivative, d squared x dt, was 2 squared times x. So the derivative of that with respect to t would simply be 2 squared times dx dt. But then again, going back to the ODE, we know that dx dt is 2x, so we get 2 squared times 2x, or 2 cubed times x. So the third derivative of x, the third derivative of x is just 2 cubed times x. And again, we can plug in t equals 0 and get the third derivative at 0 as before. So we're going to basically plug in t equals 0 to our equation for the third derivative. So you'd get 2 cubed times x when t is 0. Again, we know that's 3. So now we get 2 cubed times 3. So this pattern continues. You would similarly find that the fourth derivative of x is 2 to the fourth times x. And I'm leaving out the steps here, but the same process. You would take the derivative of the third derivative. And so the fourth derivative evaluated at 0 would be 2 to the fourth times x evaluated at 0. And from the initial condition, we know that that's 3, so we get 2 to the fourth times 3. Well, this pattern obviously continues. And so what you find is that the nth derivative of x is 2 to the n times x, and the nth derivative evaluated at 0 is 2 to the n times x evaluated at 0, so that would just be 2 to the n times 3. And this is good for any integer n from 0, 1, 2, 3, and on. So in principle, this kind of thing can be done for any initial value problem. I mean, I've taken a pretty simple example, but the derivatives only could get harder. The basic idea would still work. You can, once you have an initial value problem, you can find out what all the derivatives of the function are doing in some sense from that problem in the using the process we just talked about. So I have a little practice problem here that I want you to try. Here is another initial value problem. Dx dt is x plus t squared, and x of 0 is equal to 1. And so what you'd want to do here is find the nth derivative of x evaluated at 0 for every non-negative integer n. And so you're just going to go through that same kind of process that we just did. And let me get you started with this, and then so we'll do a couple of steps, then I'll leave it to you to finish it off, and then I'll post the full solution after you've had a chance to work through it. So you would start in the same way. First of all, just kind of a notational point here. The 0th derivative of x is just x itself. So x super 0 of 0 is just the same as x of 0, which is 1 from our initial condition. So that would be the n equals 0 case. Moving to the n equal 1 case, you basically can just use the original initial value problem here. The first derivative of x evaluated at 0, we normally just write that as x prime of 0. That's dx dt evaluated when t equals 0. But we know what dx dt is. It's x plus t squared. So this would be x evaluated at 0 plus 0 squared, because remember, t is equal to 0 here. And then x evaluated at 0 we know is 1, right? And that comes from the initial condition here. And so the result you get there is that x prime of 0 is equal to 1. And then moving along, what would you do in the n equal 2 case? Well, first of all, you have to get some information about the second derivative. And so the second derivative is the derivative of dx dt, but we know that dx dt is x plus t squared. That's again from our ODE. And then we need to take the derivative of this. You want to remember again that x is a function of t, so the derivative here would be dx dt plus 2 times t. And now we can use that ODE again, because we know that the derivative of x with respect to t is x plus t squared. And again, that's just coming from the original ODE, which was back here on the previous slide, this guy right here. So, get my papers in order here. So we know that the second derivative of x then is x plus t squared plus 2t. And now to find out what it is when t equals 0, we're just going to plug that in. So the second derivative at 0 is dx, d squared x dt squared, evaluated at t equals 0. So I'm plugging in t equals 0 to my expression for the second derivative here. You would get x of 0 plus 0 squared plus 2 times 0. But again, from the initial condition, we know that x of 0 is equal to 1, and so we finally get just 1 here. So I'm going to let you take it from here. The next step would be to look at the n equal 3 case. You'll have first you'll want to find the third derivative of x, so that's the derivative of the second derivative. And here you would go ahead and use the expression you got in the previous step for the second derivative. We got that the second derivative was x plus t squared plus 2t. And now take the derivative of that, remembering that x is a function of t, and then plug in t equals 0 to get the third derivative at t equals 0. So have a try at that and see how it goes. As I said, I'll be posting a solution after you've had a little chance to work on it. And we will pick up from here next time. Y'all take care.